Dear students, in this session, we will discuss more about the fundamental concepts of Reynolds Transport Theorem, which is very important for the fluid mechanics point of view, as well as this is the very basic concept for the computational fluid dynamics for CFD. So before entering into the Reynolds Transport Theorem, first of all, we should know for what purpose this theorem has been applied and where it has been used. With respect to this, we should first of all know what is meant by closed system and open system. This one we might already studied in thermodynamics, but I'll take some 1 minute of time to explain the basic concept of closed system and open system. If I am going to have a closed system, it means there's no mass transfer. So mass in is not permitted. Similarly, mass out of the system is also not permitted. Okay. On the other hand, there can be energy transfer. There can be energy transfer to the system. It is permitted. Energy in is permitted, as well as energy out is permitted. So this is also permitted. So mostly I used to ask my students, what is the unit of energy? What is the unit of energy? They used to tell the unit of energy as joules. The unit of energy is what? Joules. Then I used to ask them, what are different types of energy transfer you know? Then they immediately tell it is heat transfer. That's right only. Heat transfer, the unit is what? Joules. Then I used to ask the students, what is the another type of energy transfer? Mostly they'll tell only heat transfer, because energy transfer means they always feel heat. But I used to ask the question like this, what is the another quantity which has the unit as joules? Then some students will reply, as you are telling, it is nothing but work transfer. It is nothing but what? Work transfer. Why work transfer? Because the unit of work is also what? Joules. So whenever I am telling this energy transfer to the system, let it be the system. Let it be the system. And this is nothing but of my surroundings. So there is a energy transfer to the system. Either this energy transfer to the system may be in the form of heat or work. So don't feel that it should be only in the form of heat. It may also be in the form of work. That is what I want to tell. Similarly, the energy is taken out of the system can be in the form of heat or also work. So this is what I want to mean when I am telling about a closed system. A closed system is a system in which mass transfer is not allowed and only energy transfer in the form of heat or work or both can take place. That is nothing but what? Closed system. This is nothing but what? My closed system. Then what will happen to the mass inside the system? You are right. Yeah. The mass inside the system will remain fixed. So the closed system is always called as fixed mass system. Fixed mass system. So the closed system is always called as what? Fixed mass system, or the mass remains constant in the system. It will not vary. It will be always same. Let us say if it is a 5 kg of air is there. So before the beginning as well as the end of the process also, it will be 5 kg only. That is nothing but what? Your closed system. And generally students they are unable to imagine what is a system. A system is nothing but a place in a space or region in space or a particular quantity of matter where you want to apply the laws of thermodynamics. Why you want to apply the laws of thermodynamics? Because you want to study about that. Because you want to study about this. So what I can assume as a system, for example, I can assume whatever the air molecules within my palm as my system. There's nothing wrong in that. But I want to study how much of mass is entering in or how much amount of energy is being transferred is being taking place because to the system. Or I can take this entire room where I am recording this video as my system. I can take this entire city as my system. Or I can take a piston cylinder assembly. If I'm going to for engineering application, if I'm going to have this is nothing but my cylinder, this is nothing but my piston. So if I want to study about the properties of this particular fluid, then that is my system. It's IC engine is my system. Gas turbine combustor is my system. Blower is my system. So wherever you want to study, that is nothing but what is called as your system. So don't imagine system is too much. System is nothing but where you want to concentrate. So a closed system is nothing but a system of fixed mass. The mass remains constant. And one more point is that the same mass remains always. The mass will not vary. The mass will not vary. The same mass, the same molecules will be there within the system. That is nothing but what? Closed system. The very good example of a closed system, I will erase this one. The very good example of a closed system is nothing but my piston cylinder assembly. So if you can take, this is my piston and this is my, this one is nothing but my piston. These three things are nothing but my cylinder. And here some amount of, let us take the working medium as air. This is nothing but what? Air. Now it is closed system because the air cannot, the already air is there. This air cannot go out, or some amount of air cannot from the atmosphere cannot enter into this system. The mass of this air within the system remains constant. The mass of the air within the system remains constant. Then, so mass is fixed. But there should be energy transfer. How we can add energy to the system? By if we can even heat the boundaries of the cylinder, so the heat transfer will be taking place across the boundary, and as the air molecules get heated up, just the energy transfer is there. No, sir, I don't want to apply the energy transfer in the form of heat. I want to apply the energy transfer in the form of work. Then what you do? You please move this piston inside. It is compressing the air. It is compressing the air. Now the energy transfer is taking place inside the system. When I'm going to move the piston outwards, then work is done by the air on the piston. So that is also what? Energy transfer. So we can see this example of piston cylinder assembly without any walls and a fluid contained within the piston cylinder assembly is an example of a closed system. Here the mass remains fixed, whereas the energy transfer takes place either in the form of heat or work. Here we are not considering the heat, we are going to consider the work. Or if you want, you can consider also, nothing wrong in that. So this is nothing but my closed system. And let us come to the open system. Can anybody now tell what is by open system? Open system. So closed system means mass transfer is not permitted and energy transfer is permitted. In case of open system, both are permitted, which means mass transfer also take place as well as what? Energy transfer also take place. So I will take a device namely called as the convergent nozzle. So if you can have like this. So this is nothing but a convergent nozzle. So here for the convergent nozzle, now what is coming? Let us assume the steam is coming. Let us assume the steam is coming at the inlet. Let this be the inlet, say 1, 1. And the outlet is here at the exit, say 2, 2. Say 2, 2. So steam is going to enter in and leave. So here, which is my system? I am going to imagine a control volume surrounding this, very close to this one. So we can see this is nothing but my control volume. So within this volume is nothing but my control volume. It's not actually real. It's an imaginary control volume. We are going to imagine a control volume through which the steam is going to enter and leaves. So here we can see mass in is permitted. Similarly, what is permitted? Mass out is permitted. So here we can see there's a mass transfer is allowed. Mass transfer is allowed. Along with the mass transfer, there can also be energy transfer. What is energy transfer? You can add heat to the system. You can add what? Heat to the system. Or you can add work to the system. Okay. Generally, we will not add work. Generally, the steam has the enthalpy energy. So in this case, the heat is added to the system. So there's a energy transfer also taking place. So we can see in an open system, both mass transfer and energy transfer takes place. In case of closed system, only energy transfer. So it's here is what? Only energy transfer. Whereas in an open system, both mass transfer and energy transfer take place. Generally, I used to ask my students, given an example, an engineering example of open system. Then they used to think a lot. Then I used to tell all the devices of engineering equipments are open system in nature. For example, you take the fan in this room. This is nothing but an open system because the air comes in, it gets rotated, it leaves. Our air conditioner is there. That is also an open system. Why? The air is taken from the atmosphere, it is been cooled and sent inside this room. So it's an open system. You take an IC engine where fuel and the air enters into the combustion chamber, get mixed, burnt, and once again is going through away. It's nothing but what? Exhaust. So there's a mass in, there's a mass out. There's an energy transfer both in the form of heat and work. Why there's a heat? Because of the combustion of the fuel with the air. This is why heat transfer. What is the work transfer? Because of the combustion, it will push the piston downwards. So there's a what? Work transfer. So you can see even this convergent nozzle is an example of an open system because both mass transfer and energy transfer take place. Compressors, blowers, fans, pumps, turbines, heat exchangers, all devices of engineering applications are open system in nature. So first of all, before going to Reynolds Transport Theorem, we have taken much time to understand what is meant by closed system and open system. Closed system is nothing but a system in which the mass remains constant. Here the mass need not to be constant. Okay, when the mass remains constant, when the flow rate is steady. What is meant by steady? If 5 kg per second is going to come always, then 5 kg per second of air will leave, steam always leaves outwards. Then it is steady. Then it's called what? Steady. It is not going to vary with respect to time. The mass rate at inlet and the outlet remains same. This is coming out of because of the conception of mass principle. Nothing but what? M dot 1 equal to M dot 2. The mass flow rate at the inlet should be equal to the mass flow rate at the exit. Okay. On the other hand, the first transient, the flow is what? Transient means the flow will fluctuate. So instead of 5 kg, next time it will come 5.1. So the output will also be what? 5.1. Sometimes it can go for 4.8. The outcome also will be what? 4.8. Which means the input is keep on varying with respect to time. This type of analysis is called as transient analysis. This type of analysis is what? It will vary with respect to time. But generally, we can restrict ourselves to steady state. Steady state means what? Here also 5 kg, here also 5 kg. Always we are going to retain 5 kg per second at always. So it is going to be steady state. Now let us say in a closed system also, I am going to have 5 kg per second of air. Now you can see the system is always having 5 kg of working fluid. This system is also always having what? 5 kg of working fluid. So both are same. This question is arising in our mind. Because here also the mass is fixed, here also the mass is fixed. But there is a small difference between this closed system and open system. Can you tell what is that? Here also the mass remains fixed at what? 5 kg. Here also the mass fixed at what? At any instant of time, the mass inside the system within my control volume will be what? 5 kg. Then what is the difference? Here the same molecules is retained. Here some molecules enter and leaves. Some other molecules come. Even though both are air, but it's not able to retain the same molecule. Some amount of air molecule is coming, some amount of air molecule is leaving. But here we are retaining the same molecule. This is given by a term called as identity. This is given by what? Identity. Even though the mass remains same in both cases, but the same molecule is not there. Even though they are air, they are what? This molecule will leave away. There's some other new air molecule will come. So that term is called as identity. So we can see in case of closed system, the identity is maintained. Whereas in case of open system, we can't maintain the identity because even though it's air, different molecules enters and the same amount of mass is leaving. That is the difference between the open system and the closed system. With the following this one, I will continue with the next section. Dear students, let us continue with the discussion on Reynolds Transport Theorem. In the previous session, we had discussed about the closed system and the open system. In case of closed system, there is only energy transfer and there is no mass transfer. In case of open system, there is both mass and energy transfer. So with that respect, we see an open or a control volume approach is required for capture the physics in an open system, and a control mass system is required for capturing the physics in a closed system. The Reynolds Transport Theorem is going to give a connection between the control mass system and the control volume approach. That one we are going to discuss and we are going to continue from the previous session. Let the control system at time t is represented by this blue color curve. Let it be control system. Whenever I'm telling control system, it's called as control mass system. So you can understand that the mass inside the system will remain the same. It will not vary. It will remain the same at time t. Sometime we'll call this as control mass system, and sometime we'll call this as control system. It's enough to indicate as control system. There's no need to indicate further as a control mass system. So these are time t. What happens means when these fluid molecules are there, the fluid molecules are trying to move, and hence this control system also tries to move and try to capture all the fluid molecules within it. So I can put you like this. So this is nothing but the same system. This is also control system at time t plus delta t. So when time t equal t, the initial control system is at a blue color curve, and when the time is t plus delta t, after an incremental time, the control system occupies a new position, and which is given by the red color curve, and is known as control system at time t plus delta t. Now you may wonder why the shape of the control system may vary. Yes, the shape has definitely varied. Earlier the shape is like this. Now the shape has taken another dimension. What is the objective is that why the shape has changed is that this control system or this regular curve should encompass the same fluid particles. For example, here I have some 2 kg of air, and this 2 kg of air is moving. For example, I am telling, when this 2 kg of air is moving and it may spread here and there, but this control system should be in a position, it can expand or it can contract such that it should have the same 2 kg of air molecules, so that we have given the liberty that it can have variation in shape. So that is the shape what I have shown in the red color curve. I hope now why the shape of the control system have been varied. And yesterday we have seen the properties, namely N as the extensive property. So I can tell enthalpy, internal energy, entropy, volume, these are all extensive property which doesn't depends upon mass, which depends on mass. For example, if I'm going to burn 1 kilogram of diesel, I'll end up with 44,000 kilojoule of heat energy. So, for example, I'm going to burn 1 kilogram of diesel fuel with the air. What is the amount of heat content in the diesel is nothing but 44,000 kilojoules. Okay. Or we can put as 44 megajoules. What will happen if I'm going to burn 2 kilogram of diesel? Automatically everybody knows it will be what? 88 megajoules. It will be what? 88 megajoules. So here we can see as the mass increases, the property also changes or varies. This is called as extensive property. Extensive properties are those properties which depends on the mass. If the mass increases, the property also varies. Similarly, your internal energy. Okay. Similarly, your entropy. The unit of entropy is kilojoule per Kelvin or joule per Kelvin. The unit of volume is meter cube. The unit of internal energy is what? Joules or kilojoules. Okay. These and all called the extensive property. Now I can give an example for an intensive property. What is the intensive property? I'll tell density as an intensive property. I'll tell pressure as an intensive property. I'll tell temperature as an intensive property. Why? If I'm going to have 1 liter of water, what is the density of 1 liter of water? 1000 kg per meter cube. 1000 kg per meter cube. Instead of 1 liter of water, I'm going to give you only 100 ml of water. I'm going to ask you what is the density of water. Still, you will be telling the density of water is what? 1000 kg per meter cube only. So from this, what you understand is that this property, namely the density, doesn't vary with respect to the mass of the substance, and hence they are called as intensive. Intensive is nothing but INTNSIVE. Intensive properties are those properties which are independent of the mass, whereas extensive properties are those properties which are dependent on the mass. So we can see the intensive properties are independent of the mass. The examples are pressure, density, temperature, etc. Now there's a possibility this extensive property may also become intensive property. When? I am telling once again, this extensive property may also become intensive property when? Instead of considering 2 kg or 3 kg or 4 kg, if I am going to consider per kg, if I am going to divide per kg, the value will be constant. It will not depend on mass. Then that particular quantity is called as what? Specific extensive property or intensive property. I'll give an example so that you can understand better. Don't worry. Okay. What I'm telling is that I'm going to have small h. What is small h? Specific enthalpy. What does it mean? What is the amount of heat liberated when I'm going to burn per kilogram of fuel? So instead of 5 kg of diesel or 10 kg of diesel, I'm going to take only per kg of diesel. So it will be what? Capital H by M. It will be what? 44 by 1. So it will be what? 44 megajoule per kilogram. So now the unit is not megajoule. Now the unit is become what? Megajoule per kilogram. Megajoules per kilogram. Similarly, the internal energy also what? Small u will become what? Capital U by M. Which is also the unit will be what? Kilojoule per kilogram. Yearly the unit of entropy is what? Kilojoule per Kelvin. Now the unit of specific entropy. Whatever I am telling in the right hand side is nothing but specific quantities. Specific quantities means what? Specific enthalpy, specific internal energy, specific entropy is nothing but capital S by M. So what unit it is? Kilojoule or joule per kilogram Kelvin. So we can see the extensive property can be made as intensive property when you are going to divide by the mass. When you are going to divide by the mass or per kg of the substance considered. Per kg of the substance considered. So what the commonality you find between these two things is nothing but all the extensive properties are given by the letter capital letters, and we are going to give the extensive property as capital N. We are going to give the extensive property as what? Capital N, because all the extensive properties are given by the capital letter. Where the small intensive properties are, I can't even tell intensive, I can tell as specific extensive, which is also called as intensive. These specific extensive properties are intensive properties given by small letters. So this will automatically become small n. It will automatically become what? Small n. Okay. Now what are the relationship between capital N and small n? Can you tell me? What are the relationship between capital N and small n? So n will be what? Capital N by mass. So we are right. You are right. So we can see that small n equal to capital N by M. So these are the three properties I want to just mention you now. So what we are going to concentrate with respect to the extensive and intensity property, let n can be, capital N can be any extensive property and small n be the corresponding intensive property. The relationship between the extensive property and the intensive property is something but small n equal to capital N by M. Capital N by M. These are the three things which you want to know. I have given more example to make it more clarified. Okay, yeah. So it is capital N and small n and M. What is capital N? It is nothing but your extensive property. What is small n? Intensive property. What is M? Mass. Now let us discuss what is dx by dt. Can I write dx by dt as x2 minus x1 divided by t2 minus t1? Whether I can write dx by dt as x2 minus x1 by t2 minus t1. What is the difference between these two terms is nothing but the left hand side is the differential form. The left hand side is what? Differential. Maybe the school students up to 10th standard, they will be studying in the present standard, but the engineering students will be well aware of this differential term. The right hand side is nothing but the difference term. The right hand side is nothing but the difference term. Both are not actually equal. Both can't be actually equal, but we'll try to make it equal. Otherwise, it's called as equivalent. It is called as what? Equivalent. When the limit t2 tends to t1. When the limit t2 tends to, when the limit t2 tends to t1, then x2 minus x1 by t2 by t1 can be equated to what? dx by dt. That is the difference of time between t1 and t2 should be almost 0, but not practically 0. Because 0 means there is no value. So the idea is that the difference between t1 and t2 should be negligibly small such that it approaches 0, but not 0. But not 0. Then I can tell x2 minus x1 by t2 minus t1 as what? Dx by dt. I can tell as what? x2 minus x1 by t2 minus t1 as what? Dx by dt. Otherwise, if I have d phi by dx, how can I write this d phi by dx? Another example I want to tell you so that you will feel more comfortable. So what is d phi by dx? Phi is any property. Phi is any property. Here x is the property. Here phi is the property. So what is phi? How can I write in difference form? It will be phi 2 minus phi 1 divided by x2 minus x1. Both are not equal. When will be they equal? When the limit x2 tends to what? x1. When the limit x2 tends to x1, then phi 2 minus phi 1 by x2 minus x1 will be equal to d phi by dx. Here, what is x1 and x2? Here, this is the point x1. This is the point x2. This point x2 should be much closer to x1. Instead of here, it is better to be here. Instead of here, it is better to be here. So, as much close as x2 to x1, then both are almost equal. Both are almost equal. So, now you know what is the differential form. What is the difference form? When the differential form will be almost equal to the difference form. Or I can put it other way, other term. When the differential form will be almost equal to the differential form. Will be almost equal to the differential form when the limit in the denominator tends to disappear. With this concept, let us try to move further. So this concept you should know in your basic stuff so that you can implement this stuff to arrive at the Reynolds Transport Theorem. I will now tell. This control system is given by blue color is given at a time t, and this control system has taken a new shape of red color at time t plus delta t. At time t plus delta t. Why it has taken a different shape? Because it has to take the same amount of molecules. It should not leave away the molecules. Already we have discussed. So I don't waste much time. Now the common area between this red color curve and the blue color curve is my control volume. So what is the common area you can see here? What I am going to draw over the red color mark with the black color sketch. So this area is nothing but my control volume. So whatever I have drawn in the black color curve, which is common to both the blue color curve and the red color curve, is nothing but my control volume. And let us indicate this region by a Roman letter 2. And the region from which the flow happens outwards or outflow from this domain, let us call this particular domain as domain 3 or region 3. Similarly, the region is coming inside the control volume. This region is going out of the control volume. Now this coming inside the control volume, let us define that particular domain as region 1. So I will repeat once again. The blue color curve is the control system volume at time t, and it takes a new shape as in red color at time t plus delta t. And the thing is, the t plus delta t, the delta t should almost approach 0, which means the red color curve should be almost merging with the blue color curve. That is the idea. Why? Because the delta t is almost 0, but not 0. So your idea is that the red color curve should almost merge with the blue color curve, but should not merge. So in such a case, the common area between the blue color curve and the red color curve is nothing but my required control volume. So you can see the beauty that the control volume has been emerged as a result of control system. The control volume has emerged as a result of control system and is moving between the time t and t plus delta t. This control volume, you can see the beauty, it is fixed. It is what? Fixed. The control volume is fixed when the control system is moving between the time t and t plus delta t. That is, you should get into the picture. Okay, and we have defined the common domain as 2, and which is going out of the control volume as 3, and is getting inside the domain as what? 1. Okay, let us now define dn by dt of the system. What is dn by dt? What is first of all n? N is nothing but the extensive property. What is d by dt? The rate of change of the extensive property with respect to the control system. With respect to the control system means what? Either blue color curve or red color curve, or not the black color curve, or not the black color curve. Okay, so I will repeat it. First of all, when I am writing some mathematical expression, you should understand the physical meaning of it. So I have written here dn by dt of the system or the control system is nothing but the rate of change of anything divided by time is called as rate. The rate of change of which one? The extensive property of the control system when it's moving from time t to t plus delta t is given by is equal to. How we can write this one in the difference form? How we can write in the difference form? Just like I told now, dx by dt equal to what? x2 minus x1 by what? t2 minus t1. Like this, I want to write this one. Like this, I want to write this term also. dn by dt of system. How we can write? Then when I asked my students, they told it is n2 minus n1 by t2 minus t1. It is not n2 or n1. What is n2 is called as n at, it is going to vary with respect to space only. N at what? T plus delta t minus n at what? T. So here the difference in the control system is happening because of the time when it's moving from time t equal to t and time t equal to t plus delta t. So we have to write as what? N of t plus delta t minus n of t divided by delta t. This delta t is nothing but what? T2 minus t1. Otherwise, if you want, you can put as what? Delta t also. Both are same. Delta t is nothing but what? T2 minus T1, like this. Like this. So I hope you are able to understand how I have written as what? Why I have not written as N2 minus N1? Because N2 minus N1 is with respect to spatial coordinate. Now we are writing with respect to time, because we are differentiating with respect to time. So N of T plus delta T minus N of T by delta T. Still it is not over. Why it is not still over? Because I told the differential operator will not be equal to what? Difference operator. Then I have to put the limits. The limit delta t tends to 0. What is meant by delta t tends to 0? That is, what is delta t? T2 minus T1. When this will become 0? When T2 will be equal to what? T1. That's what we used to put earlier. When T2 tends to T1. Instead of that, I am putting as what? When delta t tends to 0. Both are same. Whatever way you want, you can take it. So it is a way of expressing. Now, I hope every one of you is able to understand how I have written dn by dt of the system is equal to limit delta t tends to 0, n of t plus delta t minus n of t by delta t. I hope it's very clear. It's not a doubt. Okay. I'll once again explain. The rate of change of the essential property n when the control system is moving between the time t equal t and t equal t plus delta t is given by n of t plus delta t minus n of t by delta t. This will be equal only when the limit delta t tends to 0. I hope you got it. Further we'll move. Okay, further we'll move. Now, what is n of t plus delta t? At t plus delta t, what is the volume is here? You can see this one I put as what? Time t plus delta t. So, what is the region it is occupying? It is occupying the region 2 and 3. Please make a note. When the time is t plus delta t, the region occupied by this system is what? 2 and 3. When the time is t, what is the region is occupied? This is the blue color curve. It will be 1 and 2. So I hope you are able to understand. So when the time is t plus delta t means it is this curve. I have indicated what? T plus delta t, which is about 2 and 3. That is a red color curve. And when the time is t means it's blue color curve, which is about what? 1 and 2. So t plus delta t means it is 2 and 3. Comma, when time equal t means what? This blue color curve, which is nothing but what? 1 and 2. So I am going to expand further the right hand side. I am going to expand further the right hand side. So it is limit delta t tends to 0, n of 2 comma t plus delta t plus n of 3 t plus delta t. Why? Because of t plus delta t we have both 2 and 3. So I have written both addition minus What is n of t? At n of t I have 1 and 2. So I can put the minus as common. N of 1 comma t plus n of 2 comma t by delta t. Here the only step what you have to understand is nothing but how I am able to write this 2 and 3 and 1 and 2, then it's further easy. I hope I can erase and move further. I hope I can even erase this one because of the space constraint. Otherwise, I will write this as t plus delta t. Red color covers what? T plus delta t. What on the left hand side is dn by dt of system. Okay. Now, I am going to take the first term and the fourth term. Why I am taking the first term and fourth term? Because both are corresponding to the region or the domain capital Roman letter 2. Capital Roman letter 2. So, I am going to choose the first term and the last term and I am going to combine them together. I am just working mathematically. N of 2 comma t plus delta t minus, why minus? This minus will be taken here, minus n of 2 comma t by delta t. What on the left hand side? You don't forget about the left hand side is dn by dt of the system or the control system or the fixed mass system, and it's going to move from t to t plus delta t. Okay, the remaining terms we can write plus n of 3 comma t plus delta t minus n of 1 comma t by delta t. So just I rearranged it. I have rearranged it. First I have taken 1 and 4 and written here. Then I have taken 2 and 3 and I have written here. That's it. Now both are 2. Now both are in this first things. Both are what? 2. One is at t plus delta t, another is at t. Let us not worry about that. Now what is the domain 2? You see the board. What is the domain 2? The domain 2 is nothing but your control volume. The domain 2 is nothing but what? The control volume. As I told you earlier, the control volume is fixed and it emerges because of the movement of the control system. That is the beauty. So we can see this term is nothing but, now what is this one? Any property which is going to change with respect to what? Time is the rate. So here I have in the form of, one more thing I have missed here. What is one more thing I missed here? I have to always put limit delta t tends to 0. Here also what I have to put? Always I have to put limit delta t tends to 0 for the second, third and fourth term. Similarly for the first and fourth term, here second and the third term. Okay, fine. Now we can see here, this term, this is in the form of difference form. I am going to take in the form of differential form. I am going to put back in the form of differential. So I am going to write as, so if it is going to be in the difference form, how can I write in the difference form? I can write as dn by dt of the control volume. Why it is control volume? Because the domain is 2. 2 means what? Control volume. So otherwise I can turn like this. If I write dn by dt of the control volume, how I will be writing this one? N of t plus delta t of 2 minus n of 2 comma t by t2 minus t1 or delta t. When the limits t2 delta t tends to 0. This one only will write. Now from this one I am moving to this one. So from this one I am moving to this one. I hope you will be able to understand. Now I am trying to write back from the difference form to the differential form. From the difference form to the differential form. So it will be dn by dt. But this is not the control system because it becomes a domain is 2. Domain is 2 means what? It is control volume. So I will indicate as control volume. But in the book, instead of dn by dt, they may given dou n by dou t. They may given us what? Dou n by dt. Instead of differential equation, they may given us what? Partial differential equation. They may given us partial differential equation. So you may wonder why instead of d I have given us dou. The beauty is that the control volume is fixed. The control volume is not moving. So it will vary only with respect to time and not with respect to space. So I want to give a difference between this capital D n by dt and dou n by dt. Here the n, the essential property, is not only varying with respect to time, but also is varying with respect to space. But also varies with respect to what? space. This dn by dt is called the substantial derivative or the total derivative, where n is a function of x, y, z and t. When this is a function of x, y, z and t, when I'm going to have d by dt. When I'm going to have only dou by dou t, then n is a function of only t. Then n is a function of only what? T. So there is no need to go for dn by dt. It's enough to go for dou n by dt. Why you are going for only dou n by dt? Because the control limit is not moving. So it's not going to vary with respect to space. It is going to vary only with respect to time. I hope you got it. Okay. So I have given the reason why I am not using d. I am using only dou, because the control limit is fixed. It is not going to vary with respect to space. It is going to vary only with respect to time of this control volume. So the left hand side is what? dn by dt of the system. What is this n of 3 at t plus delta t? What is first of all n? N is nothing but efficiency property. When efficiency property is divided by time, it is nothing but the rate of change of efficiency property. Okay. And what is n of 3? This is the domain which is coming out of the control volume. It is coming out of the control volume. So I can tell this time is rate of change of efficiency property, extensive rate of change of efficiency property. Since it is 3, instead of rate of change of, I can even tell us rate of outflow of efficiency property. Rate of outflow of efficiency property. How the efficiency property is coming out of the control volume, because the domain is what? 3. This one is for these two things. When I am taking this one, the corresponding expression is nothing but rate of outflow of efficiency property from the control volume is given by this particular term. What about this term? Can anyone tell what is n of 1 comma t? What is one domain? This domain. And is with respect to the control volume. So it's nothing but what? This is also rate of change of the efficiency property. But instead of outflow, it is inflow, because how much property is entering into the control volume. So I can tell it is nothing but rate of inflow of efficiency property. Rate of inflow of efficiency property. So these two terms are there. Okay. So the rate of outflow of efficiency property, that's the domain 3, because rate means divided by time. So this n is nothing but what? Efficiency property with respect to the 3 means outflow. 1 means inflow. Okay. So finally, how many terms are here? There are 2 terms. But whether there will be 2 terms? No, there will be only 1 term. Why? For example, if I am going to give 5 kilogram, here I can expect 6 kilogram of air is coming. For example, I am telling. Whatever I am telling is only for your understanding. For example, the inflow is 5 kilogram per second. I am getting 6 kilogram per second. Whether it's possible? Yes, it's possible. Which means, so 1 more kilogram is been obtained from the control volume. So the mass within the control volume will decrease. The mass inside the control volume will decrease. On the other hand, I am sending only 5 kilogram. I am getting only 4 kilogram. What does it mean? 1 kilogram of mass has been accumulated inside the control volume, which means the mass inside the control volume will increase. The mass inside the control volume will increase. So this value will become only 1 term. This outflow minus inflow will be either positive. When it will be positive? When the outflow is more than the inflow, it will be positive. When the inflow is more than the outflow, then it will be negative. Then it will be negative. So don't feel this is a 2 term, it's only 1 term. Now this particular expression is nothing but, my Reynolds Transport Theorem. Why is called as Reynolds Transport Theorem? Which connects the rate of change of a efficiency property of the control mass system to that of the what? Control volume approach. To that of the, this is a control system or fixed mass. This is a control volume approach. Plus some mathematical terms. If I am further going to expand what is this one and what is this one, our derivation will come to an end. So if you are able to expand what is done by dot of control volume plus this particular term, our problem will be solved. Okay, fine. Shall we continue further? Yeah. Okay, already we know that small n equal to capital N by M. So from this, what is n? N will be equal to n into M. So I can replace this capital N as what? N into small m. You can please recall the topics between the extensive property and the intensive property. You will get this answer. N equal to n into M. Now, out of this control volume, I will be taking a elemental control volume. Let this elemental control volume is going to be this blue color region. I will repeat once again. The domain 2 indicates the control volume. Out of this control volume, the blue color curve indicates me the elemental control volume. So this black color curve indicates the control volume and this blue color curve indicates the elemental control volume. What is the meaning? If I am going to integrate this control volume with respect to the thing, I will get this entire control volume. That is the meaning. So if I am going to do a triple integral, then this elemental control volume will become what? The full control volume. Okay, that's the meaning. That's the idea. Okay. Now, what is the mass of this elemental control volume? I want to know the mass. I want to know the mass of this elemental control volume. What is the formula for density? Density equal to mass by volume. So mass will be equal to what? Density into volume. Density into volume. Here we will indicate the volume as like this. Like this. Okay. To differentiate. Okay, fine. Now, this is not the mass of the entire control volume. It is the mass of the only the elemental control volume. So, the M can be equal to rho into dV. Why I am putting dV instead of V? Because that is the volume occupied by the elemental control volume and not of the entire control volume. So, it's only the elemental control volume. So, it is rho into dV. Now, I got what is M. M is what? Rho into dV. If I want to find the mass of this entire control volume, then what will do? Now the mass of the elemental control volume is nothing but rho into dV. Now if I want to find the mass of this entire control volume, what do you have to do? You have to integrate. We want to find the mass which is occupied on the entire control volume. So I have to do a triple integral. So what is that meaning? Means I have to do a triple integral rho dV. Then this will give me what? The total mass. This will be giving me what? The mass of the elemental control volume. Whereas this term will give the mass of the entire control volume. Mass of the entire control volume. I hope you got it. I hope you got it. Okay. Now what I am about to tell here is that I am going to replace this n with what? This particular m into n. M into what? N. What is now m? M is nothing but this one. What is n then? I have to multiply by n. That's it. I have to multiply by n. I will repeat once again. I want to find dou by dou t of n. First of all, I want to find n. What is n? N equal to n into m. First of all, I have to find m. What is m? M is the mass of the control volume. But I am going to find the mass of the elemental control volume, which is given by rho into dV. Where dV is the volume of the elemental control volume. If you want to find the mass of the entire control volume, then I have to integrate. So, triple integral of rho dV will give me the mass of the entire control volume. If I want to multiply the mass with n, I will get the capital N. So, I am multiplying n with the mass, rho dV. So, I can take as for n as what now? I can replace the n as what? Triple integral of n into rho dV. Triple integral of n into rho dV. Because this is a specific extensive property. This is the mass. Whenever I multiply, it becomes extensive property. I hope you got it. I hope you got it. So I can write this term as dou by dou t of, instead of n, I can put a triple integral of n into m. N is n. M is nothing but what? Rho into dV. Here the V indicates what? The elemental control volume. Here the V indicates the control volume. So this, what is the left hand side? At the end time, as I told you, don't forget about the left hand side. It is the dN by dt of the control system. In some book or in most of the books, instead of this triple integral, they will give only a single integral. Whether it's right or wrong, definitely it's wrong because it will be triple integral. But we will indicate the triple integral as a formula called as CV. So integrate over the entire control volume. So it automatically become what? Control volume. So instead of representing this triple integral, you can also integrate, you can also show us what? Both are same. Both are same. Why I want to show like this means I am trying to move from a control mass system to a control volume approach. So this will be more appropriate than using a triple integral. I hope you can appreciate and the usage of single integral with the CV. It's not single integral. It actually means a triple integral only. But here control volume is there. So dou by dou t is already there. I am just replacing for n as what? Control volume integral of n into rho into dv. So we are happy that we are almost completed 85%. We are left only with the last two terms. They are not two terms, they are only one term. It will become positive when the outflow is more than the inflow. It will become negative when the inflow is more than the outflow. Very good. So this term is also over. Just now we have to work on the term which have been written in this formula. Okay, formula. Okay, fine. I hope I'll erase it and I'll bring it back. Okay, I hope I'll, because of the space constraint, I'll erase it and bring it back. So we are going to work on only this term because already this term is derived as dou by dou t of single integral of control volume n into this one. Yeah. So we are left with only the last term, which is nothing but rate of outflow minus rate of inflow. Here, what is n? Whether n is mass? No. N can be anything, any extrinsic property. It can be mass also, momentum, energy, enthalpy, internal energy, entropy, volume. So n can be any extrinsic property. Okay. Now rate of outflow of extrinsic property. Some property is coming and leaving out of this thing. Then how to find that one? So now you can see, all of you can see, these properties existing are going out through this control surface. Whatever I have shown here in the red color mark is going to come out of this control volume through this red color mark, isn't it? So I am going to draw, for example, if I am going to draw like a circular one for your understanding. In the circular one, this is the domain where it's going to come out. So I will take that particular domain as this one. So out of this entire control volume, there is a small control area or control surface through which the outflow of a property happens. Outflow of a property happens. Then this is the entire area, out of which I am going to take only this area from here to here. Okay, then let this area be dA. Why I put dA? It's not the entire control surface area. It is only the area, elemental control surface area. Elemental control surface area. Which will be coming now? Some essential property is coming. It's coming means what? It has some velocity. It's coming out means what? Without velocity it can't move. So it's coming means it's coming with a velocity. So that velocity, I can call that velocity as V bar. I can call that velocity as what? V bar. I am telling some essential property is coming and coming out of the control volume through the control surface. This particular control surface. Out of this control surface, I am going to take elemental control surface, that is dA. Okay. Now it's coming out means what? It should come with some velocity. Let the velocity be V. Generally, this V is nothing but what? The relative velocity of the flow or the relative velocity of the property with respect to what? The control volume or the control volume. Now, there is actually this eta is there. This eta is nothing but the unit vector normal to this direction of coming out of the property. So eta is nothing but the unit vector normal to the flow. This unit vector will not remain same. It will keep on varying along the all three this direction. So in the other hand, if I going to take another area where there is another dA, now this eta will be opposite. If I going to consider this eta as positive, means this eta will become negative. This eta will become what? Negative. So this is a unit vector. This n cap indicates a direction. So in physics, the positive or negative will indicate only the direction. So there's no need to worry about the magnitude. But the direction is also important. So we are considering when it's coming out as outflow, we are considering the unit vector as positive. When it's going to go in the other direction, it will be negative. It will be called as what? Negative. So why we want to discuss all these terms? Because we want to arrive at this formula. We want to arrive at this formula. All of us will know the mass flow rate m dot will be equal to rho AV. How this defined? density equal to mass by volume. What is mass? Density into volume. Volume means I will put as capital V with a strike mark. So what is volume? Volume is nothing but area into length. Area into length. This is mass. So do it both sides by time. So it's m by time is nothing but m dot. Mass flow rate. Until here the unit is kilogram. Now the unit become what? Kilogram per second. Kilogram per second. So it will become rho into area into length by time. What is length by time or distance by time? Is nothing but velocity. Is nothing but what? Velocity. So this m dot will become rho a into v. This v is nothing but velocity. Okay. So this is the formula for the mass flow rate. The formula for the mass flow rate is something but rho a v. Rho a v. Where rho is the density, a is nothing but the area, and v is the velocity at which it is flowing. Okay. So mostly our school also we will discuss like this. M dot 1 equal to rho 1 a1 v1, which will be equal to what? Rho 2 a2 v2, which is nothing but equal to what? Your m dot 2, where v1 v2 are the velocities, where v1 v2 are not the velocities, are not the volume, This is nothing but what? Consideration of mass principle or continuity equation, or corresponding the equation is called as what? Continuity equation. The principle is called as what? Consideration of mass. Okay. So we see this is what? The unit is kilogram per second. The unit is what? Kilogram per second. Why I want to tell this m dot now? That may be your question. Why your process trying to derive m dot equal to rho 1 a1 v1, which is equal to rho 2 a2 v2? Because now rate of outflow of efficiency property. Once again, what is that? Is capital N will be equal to what? Small n into m. Because n equal to capital N by m. So n will be equal to what? N into m. So first of all, I have to find what is m. First of all, I have to find what is m. Now m, I have to find means I will erase this one. Yeah. When I want to find m, so what is the amount of mass which is emerging or which is coming out through this elemental control surface dA? I will repeat the sentence. What is the amount of mass which is emerging through the elemental control surface dA? Is given by mass is nothing but what? Rho AV. So it's rho. Area is nothing but not A. It is nothing but dA because I have taken the elemental control surface. V is nothing but what? This capital V. This V is nothing but what? Capital V. If you want to make it more clear, we can put as V relative also. What is going to be V relative? The outflow velocity with respect to the control volume. Or if you are able to understand this, enough to put only what? Rho V dA. One more important term is also there. What is the important term? Is nothing but eta. Why I am putting this eta? This eta can either take positive one or negative one. Positive one means outflow. Negative one means what? Inflow. That's the only reason. So this is the amount of mass which is coming out of this control volume through the elemental control area dA. So this is nothing but what? Mass. Why is mass? It's rho AV. So it's actually not mass. It's called mass flow rate. It's called what? Mass flow rate. Okay, fine. Now this is the amount of mass which is coming out of the elemental control surface. Now what is my question will be? What is the total amount of mass? So out of this entire control area, I have taken only this control area dA. So my question will be, what is the amount of mass which will be coming out of the entire control area? Okay, then I have to double integrate. Then I have to what? Double integrate. So double integral of rho V A only. What is the formula? Once again, rho AV only. Why this n cap is coming? For the direction. Okay, so this is the amount of flow which is coming out. I hope it's very simple. Rho into V bar into dA into eta. This eta is positive for outflow, this eta will be negative. These two terms will not be there. There will be only one term. Why? They will fight with each other. Which will winning will be there. Okay. The formula for this this also will be the same. It will also be the same. Only the eta will vary. Only the eta will vary. So in some book, instead of this double integral, how they will given us? They will given us single integral with control surface. What is control surface? Is double integral. It's nothing but what? Double integral of what? Rho into V bar into A into, sorry, dA into unit vector cap. So now we got the expression for the This term, we already got the expression for the other two terms. Now we can write the final Reynolds Transport Theorem. So to finally arrive at the Reynolds Transport Theorem, we can see here dN by dt of the system is equal to dou by dou t of control volume into rho dV into n. This is the volume, so I am putting a slash mark into n plus control surface, this double integral of rho AV, so it is velocity into dA into unit vector into n. So this is nothing but my Reynolds Transport Theorem. The Reynolds Transport Theorem says that the rate of change of any essential property of a control mass system is connected with the rate of change of any essential property of the control volume plus some mathematical term. In some book, instead of this control volume, they may give a triple integral, which is actually the meaning. In some book, instead of a control surface, they may give a double integral, that is nothing but the area integral. This is nothing but the volume integral. I hope now this Reynolds is able to give a link between the control mass system or the control system with that of a control volume approach. This is nothing but the control volume approach. Here, the essential property N may be of any transport property, because when a flow is happening, it can transport mass, it can transport momentum, it can transport energy. And other parameters like enthalpy, any essential property. So I hope you enjoyed the lecture, the physical meaning of each and every term, how these terms have been derived, and we can see the application of this Reynolds Transport Theorem in the derivation of the kinetic equation, namely the conservation of mass principle, the momentum equation and the energy equation in the further section. You can enjoy and appreciate the use of the Reynolds Transport Theorem to arrive at the governing equations of mass, momentum and energy with respect to the control volume approach. Thank you.